Okay, we're going to talk about logarithmic functions and now their graphs. Logarithmic functions are inverses of exponential functions. So we're going to look at the inverses, and an inverse function is going to be a reflection over the graph of y equals x. So if we were to put in, if we were to put in the graph of y equals x, that's just our straight line there, y equals x, and then we were to sketch this, the logarithm graph does something like this. That's going to be y equals log base b of x. And that's going to go through the point here, 1, 0. And that's our logarithm graph. That's something that you've not seen yet, but you've seen the exponential graph. The exponential graphs do something like this, and they go through the point here at 0, 1. And inverses, what they do is they swap places with x's and y's. So notice on the logarithm, you have the point 1, 0, but on the exponential, you have the point 0, 1. They just change places with x's and y's. Okay, the next part, basic properties of logarithms, just different things. We can always say that log base b, no matter what this base is. If this is a 1, my answer is always 0, and that's because if we say b, or whatever that base is, raised to the 0 power, we always get 1. Here, if our base and our argument are the same, my answer is always 1, and that's because our small base raised to the first power equals our answer of b. So again, it's working with exponents. Here, b raised to the y power is always equal to b raised to the y power equals b to the y power. And here, this log base b raised to the log base b of x is always equal to x. This portion right here, as long as that has the same base and this as this base here, those always cancel each other out. You can even think of it as log base b of x as equaling log base b of x. Base b of x. How they're really just equal to each other. So here again, that has to be your x. All right, so evaluating logarithms, log base 2 of 8 is 3, and that's because 2 to the third power is equal to 8. Here, 3 to the 1/2 power is equal to the square root of 3. And these are things that you know. 5 raised to the negative 2 is equal to 1 over 25, not negative 10. 1 over 25. 7 raised to the first power is equal to 7. And again, notice here's another great example right here where this base and this base are the same, so 11 equals 11 right here. Or you could write out log base 6 of 11 equals log base 6 of 11. All right, so now let's look and see what happens here when your x's and y's are swapped. And again, that's talking about our inverses. So here we're going to plug in -2 into f of x. So f at -2, that's going to be 2 to the -2, which is going to be positive 1/4. So now this is saying, well, if our x is 1/4, what happens if I plug in a 1/4 to this? So in other words, if I say, well, now my x is 1/4, what is f inverse of 1/4? In other words, what is log base 2 of 1/4? In other words, what this is saying over to the side is 2 to what power gives me 1/4? Well, it has to be negative to get it to flip over. And then 2 to what power is 4? Well, 2. So here I get -2. So notice you have the ordered pair -2, 1/4, for 2 to the x. But for log base 2 of x, you get 1/4, comma, -2. So it does swap your ordered pairs. And same thing if we do -1 and plug in 2 to the -1, it's going to be 1/2. So if we say 1/2 is the x value, log base 2 of 1/2, well, that's going to give me -1. That's saying 2 to what power gave me 1/2? Well, 2 to the -1 gave me 1/2. Okay, same thing over here, 2 to the 0 power. That's going to give me 1. And so what if I plugged in 1 here? That's going to be log base 2 of 1. So again, this is saying 2 to what power gives me 1? Well, 2 to the 0 power gives you 1. So again, 0, 1, or the ordered pair 1, 0. Then we have 2 to the first, which is 2, and then we would plug in 2. And so we would have log base 2 of 2. So 2 to what power is 2? And I believe that would be a 1. And then we're going to plug in 2. So that says 2 to the second, which is going to give me 4. And then over here, if we plug in 4, that's going to be log base 2 of 4. And that's going to say 2 to what power gave me 4. And that's going to give me a 2. So there's the inverses, how one x and y's are swapped. So do keep that in mind, where we're going from exponential form to logarithmic form. All right. So looking at just our common base 10 that we usually do. Now notice it's not written. If the subscript is not written, notice here it's telling you it's often dropped, then it is understood to be a base 10. So this log 100 is the same thing as having log base 10 of 100. And this is saying 10 to what power is 100? And so that power is 2. So the answer is 2. So in part B, this is saying log base 10 of the square root of 10. And I'm going to rewrite that to be 10 to the 1/2 power. So this is saying 10 to what power is 10 to the 1/2. And so you see real quick that the answer is 1/2. All right, so part C, you've got to do some swapping. This is log base 10, and how can we flip all of that over? Well, that's going to be 1,000 raised to the -1. And then how are we going to get 10,000? What is that really? Well, that's log base 10 times 10 to the 30. It's an at 3 zeros, means an exponent of 3, raised to the -1. Well, exponent raised to an exponent, you multiply. So what exponent am I really talking about here? I'm talking about a -3. And then notice this one here. These bases, those are the same. So really that whole logarithm becomes a 1. So my answer is just 10. So that one was pretty easy. Looked hard, but it was pretty easy. All right, and so working these out on the calculator, you would find the LOG button on the calculator and just type it in, press log and then 34.5. You should get 1.538. You should get here -0.367. And logarithms, remember the graph that I drew earlier? Logarithms do something like this. Notice there's no negative numbers with logarithms. It's 1, 0. When I say no negatives, there's no negative x values. Of course, you can get a y value that's negative. Look at number B. But looking at C, you can't plug in a negative x value. So this one's not defined. Or D and E does not exist. Any of that you want to put is fine. But that argument there is you can't ever have a negative there. All right, so here to solve an exponential, they want you to change this to exponential form. Again, there's that understood 10 there. So what you're going to say, I kind of call this around the world. You're going to say 10 raised to the third power equals, and then x. So 10 to the third power is 1,000. Again, if you're not sure, just let that number tell you how many zeros to write. That equals x. And so you're going to do the same thing in part B. This time our base is 2. So you're going to say 2 to the 5th power equals x. 2 to the 5th power is 32-ish, I believe. And equals x. All right, so there's how you change it from logarithmic to exponential form. All right, and so our next ones, they want us to simplify this. And so let's see, for this, let's rewrite that. That's the same thing as natural log of e to the 1/2 power. And if we move that 1/2 power down to the front, we have 1/2 times natural log of e. And natural log of e, no matter where we see it, has a value of 1. So this all ends up being 1/2. All right, so for part B, same thing here. So we're going to move that 5 down to the front. So I have 5 times natural log of e. And again, that's going to turn into 5 times 1. So my answer is 5. Now, for part C, e to the natural log of any number is just going to be that number. Because again, it's the same idea as that base. It's going to be the same as this base, and then this base are the same. So those are going to cancel each other out. So knowing that, these are going to cancel each other out. So your answer is just 4. And then our next ones, you would put natural log in the calculator. And so your calculator values that you should get is 3.157, -0.734, And just like before, you can't have that negative argument there, so it is not defined. All right, so going through these again, natural log of 1 is 0, and that's because e to the 0 power is 1. A little bit of reminder why that's e, that might help. Log base e is the same thing of x, is the same thing as natural log of x. So anytime you see ln took the place of log base e. So that's why we're seeing e over here. So natural log of e, that's because e raised to the first power is e. Right here, that again is because e to the y is equal to e to the y. Because your base down here would be e. So e raised to the y equals e to the y. And natural log of x is going to equal natural log of x on that one. I always think of it as those two just cancel each other out. That's a little bit easier to remember. All right, so the graphing of it and analysis of this, a few things that you can remember with it. There's an asymptote right here. I don't know if y'all can see that. Let's go to a little bit darker color. You will always have a vertical asymptote right here with it, and your graph is always bent to look something like this. You go through this point right here of 1, 0. Your asymptote here was x equals 0. I didn't put that in. So there's your basic graph, just like a parent function. This is a parent function, something you do need to know. Do make sure you can get this basic graph in. The domain for this is going to be from 0 to infinity. The range for it is going to be from negative infinity to positive infinity. This is a continuous function. It is continuous. It is increasing. There's no symmetry about it. There's no extremas. It is unbounded. That's important to know. You do have a vertical asymptote at x equals 0. And your limit as x approaches infinity of the function itself is infinity. All right. So take this basic function, keep it in your mind because we're about to do some shifts with it. All right, so now we're going to transform these, and the first thing I'm going to do is look at our original. Our original logarithmic did something like this, and it went through this point here at 1, 0. So for this point right here, we need to move left 2 is what's going to happen there. So if we move that left 2, we're going to go 1, 2. So we're going to have our point over here at negative 1, 0. So really we've got something doing like that. And our asymptote is also moved. So notice that asymptote was 1 back from here, this 1, it was back 1. So from that one, our asymptote is going to be back 1 as well. So our vertical asymptote is going to be back here at x equals -2. All right, so for our next one, again, here's our original. Did something like that. And right there's our original point at 1, 0. And now let's see. We are going to reflect over the y. This really is kind of tricky there. It looks like we're really going to move, well, we've got over the y. We're going to move, we want to say left 3, but that x being negative is going to change it. You're really going to move right. Do y'all remember us setting this whole thing equal to 0 and solving? If we do that, we end up with -3. And so we're moving it right 3. So I know I'm reflecting and then I'm moving it right 3. So let's move over 3. So 1, 2, 3. And let's see if we can draw this. This I can't draw so good. Oh, that's too high. Sorry, guys. That's a little bit better. I'm just going to leave it like that. So there's your logarithmic, the best I can do. And then you've got your asymptote. All right. Now let's go see our other. It's the same thing, transforming. Now, your logarithmic, it came down here and did like this as well. So 3 times that, that's just going to make that fatter, isn't it? So if we're going to do something like that and multiply it by 3, it's just going to stretch it out some. It's going to do like that. But it's still going to go through the 0.10. It just stretched it out. And your asymptote is still the same. It's still back over there. All right, and so 1 plus log. So here's our logarithm. And here's your 1, 0. But now we've got 1 plus. So that 1 plus is going to move this all up 1. So we're going to pick everything up and move it up 1. So that's going to move this up 1. So the logarithm is going to look a little bit different. It's going to be all moved up 1. And our vertical asymptote, though, is still going to stay the same.